All right, so we're chapter 8 dealt with confidence intervals for a single sample or for a single parameter. And chapter 9 dealt with hypothesis tests for a single sample or a single parameter. Excuse me. Chapter 10 deals with inference procedures for two samples. This comes up more often than arguably more often than single samples. You know, we take a sample of girls and a sample of guys, and we want to know if whatever measure is different between them. So this comes up quite a bit. Or we run an experiment and we want to see if uh, a drug is more effective than a placebo in, stopping some kind of disease or something. So first, let's review the sampling distribution for a single proportion. Center. This is the condition. If the sample was randomly selected, then the center. So this is comparing two proportions, by the way, two percentages. Then the expected value of my p hat is going to be p, the true population proportion. Means it's unbiased. If the 10% condition is satisfied, then we can use this formula to find the spread. Then the standard deviation of your p-hats is equal to the square root of pq over n. And then as long as the large counts condition is satisfied, if you remember that is n times p greater than or equal to 10, n times q greater than or equal to 10, then you know the shape is going to be approximately normal because it's a binomial that's approximately normal. All right. So what does the sampling distribution of the differences of two sample proportions look like? So this is going to be p hat 1 minus p hat 2. So in class, we kind of went through a derivation of, or a bit of a proof or justification for why these things are this. But for this video, let's just talk about it. So what is the mean or the expected value of the difference of two proportions? Well, that's just going to be the expected value of each proportion subtracted from each other. Or the mean of the differences is the difference in the means. And since the mean of the first one is P1 and the mean of the second sample proportion is P2, it's just the difference in the proportions. Don't read too much into this. I mean, this is common sense. If we're taking two samples and we're taking the difference in the proportions, these sample proportions, the difference in these sample proportions is going to be centered about the true difference in the population proportions. I feel like it sounds more complex than it is. If we were looking at an example, it'd probably be a little easier. And we will look at an example, but that's it. Spread, as long as the two samples are independent, then to find the standard deviation of the difference of two sample proportions, we add the variances of the two random variables, right? If you want to combine two random variables using a difference, as long as they're independent, then you add the variances and then you square root to get back down to the standard deviation. So again, this is a consequence of our random variable unit. But as far as for what we care about, it's just this formula right here. I'm basically going to take this standard deviation formula. I'm going to square it to get the variances. I'm going to add the variances and I'm going to square root it to get the standard deviation. So this is on your formula sheet. Shape, if the two sampling distributions are both normal and the samples are independent, then the shape of the differences of the sample proportions will also be approximately normal. And again, that's kind of a theorem that we talked about earlier, but we didn't really prove it, but we kind of talked about it and we used it earlier. So these things are going to be true, 1, 2, 3, as long as these conditions pass. First, both samples need to be a simple random sample. That assures us of the center. 10% condition, both samples need to be less than 10% of their respective populations. That allows us to use this formula here, or technically this formula here. And then normal large counts, that assures us that the two sampling distributions are approximately normal, therefore the combination will be approximately normal. And then in order to add these two, we need to have independent samples. So I call it 4 checks. These are both independence checks. And then this is kind of a center check, and this is kind of a shape check. So, as we encountered before, what happens if you don't know the true population proportions? If we still need to get an estimate for the standard deviation of the sampling distribution, then we do what's, we calculate the standard error. So when we don't know the true population proportions, then we can estimate the standard deviation of the sampling distribution of the difference of two sample proportions using the sample proportions. Okay, so again, this is the true standard deviations, but if we don't know the population parameters, we put in the sample proportions. And then this is a pretty good estimate, smiley face. This is a good estimate for that. So we don't have to do any fancy modifications in order to do that, to make that estimate. Note, we will use the sample proportions to check the large count condition. All right, so let's do this example here. The color of goldfish. Your teacher brings 2 bags of colored goldfish to class. Bag 1 has 25% red crackers. Bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. Your teacher takes a simple random sample of 50 crackers from bag 1 and 40 crackers from bag 2. Let p hat 1 minus p hat 2 be the difference in the sample proportions of red crackers from bags 1 and bag 2. What is the probability that the sample proportion of red fish from bag 1 is larger than the proportion of red fish from bag 2? Okay, so we wouldn't think that would happen since the first bag has got 25 and the second bag has got more, well, or a higher percentage anyway, 35%. We would expect our sample proportion of P2, p hat 2, to be about 10% bigger than bag 1. But remember, these are samples, so there's going to be some variability. It's possible that this sample proportions may be just a little bit light. Maybe it's like 29%. And this one maybe just happens to be a little bit big by random chance. So this would be 30%. So that would be a case where P1 minus P2 is actually a positive 1%, for instance. Okay, so the question is, what's the probability that whenever we take 2 random samples of size 40 and 50, how likely is that to happen? So first, let's find the center of the sampling distribution of p hat 1 minus p hat 2, the mean of p hat 1 minus p hat 2, or to use my earlier notation, the expected value of p hat 1 minus p hat 2, is simply the mean of p hat 1 minus the mean of p hat 2, which is simply P1 minus P2, the difference in the true proportions. It's simply 25% minus 35%, which is negative 10%. This is not, like I told you, this is not rocket science. This is just common sense, right? On average, this bag is going to have 10% more red than this bag. Find the spread. So what is the standard deviation of p hat 1 minus p hat 2? Well, we're just going to use our formula right here. Formula from the formula sheet. It's the square root of P1 Q1 over N1 plus P2 Q2 over N2. Plug the values in. 0.25, 0.75. What size was the... We took 50 out of the first bag. Plus 0.35, 0.65. Took 40 out of the second bag. So I've typed that into my calculator right here. Hit enter. 0.097. This is also known as negative 10%, and this is 9.7%. So I don't want to drag this on more than I need to, but this is an important value. What does it mean? How do you interpret it? Well, when I take samples of size 50 from bag 1 and 40 from bag 2, and I calculate the percentage of red in bag 1 and the percentage of red in bag 2, and then I take the difference in those two percentages, these estimates for the difference in my sample, for the difference in percentages, is typically going to be 9.7 percentage points off of the true value, which is negative 10%. So the true value is negative 10%. When I take my samples and calculate the difference in my sample proportions, these differences are typically going to be 9.7 percentage points away from that difference. This is the error, average error in our estimates. Find the shape of the sampling distribution of p hat 1 minus p hat 2. Well, it's approximately normal, I'm assuming. None of these did they say to check the oh, it does say to state the condition that guarantees your answer. So I guess let's do that. Both samples were random. Okay, that's what we needed for that one. For this one, we needed the 10% condition for both samples. It's always got to be doubled up now. In single samples, it was just one. Well, 50 is less than 10% of 1,000, and 40 is less than 10% of 1,000, so that checks out. And in order to add the variances, we need to have independent samples. And this is true. I'm assuming that the 50 crackers that I picked from bag 1 have no influence on the 40 crackers I picked from bag 2. These were two independent samples. So that checks out. For normality, for normality, we've got to check large counts. That's N1 p hat 1. Not p hat, I guess. N1 Q1, N2 P2, and N2 Q2. Oh, I'm running out of time on this video. We got to hurry it up. Pick it up. So this is 50 times 0.25. That's greater than or equal to 10. This is 50 times 0.75. Definitely. 40 times 0.35. Probably going to be close, but I think we're good. And 40 times 0.65. Definitely good. So we need large counts, and technically we also need independent samples. It's a little bit of a tougher sell, but technically we need independent samples so that we know the differences are going to be whatever. Therefore, it's approximately normal. Okay. Last question. What is the probability that the sample proportion, so this is actually the question that we were posed at the beginning. What is the probability that the sample portion from the first bag is larger than the proportion of red from the second bag? What is the probability that my sample proportion from 1 is greater than my sample proportion from 2? Well, I've been looking at the difference P1 minus P2. So let's make it P1 minus P2. Let's move the P2 over this way. So this is P hat 1 minus P hat 2 has got to be greater than 0. So I want to know the probability that this difference is greater than 0. Well, I can find this as long as I know the distribution is normal. Check. I know the center. Check. The center of my differences is equal to negative 10%, sorry. And as long as I know the standard deviation. And I know that one as well, 0.097. I want to find the probability that the difference is greater than 0. So that's going to be kind of about right here, or greater than that. So this is just going to be normal CDF, put those values in. If I were to estimate, I'd probably say about maybe 20, 15%. So normal CDF, I want to go from 0 to infinity. The mean is negative 0.1, standard deviation is that. Hit enter, 0.151. 0.151. So if we take a sample size 50 from the red bag and a sample size 40 from the second bag, and take the difference in those sample proportions, there's a 15% chance that the sample of red in the first proportion in the first bag is actually going to be bigger than the sample proportion in the second bag. Okay? This is a pretty complex probability question, just to let you know. Like if you tried to do this using some other techniques, it would be very, very difficult. So sampling distributions and these normal approximations make it more manageable.